Hi guys, John here again, and today we'll be continuing with Multisim tutorial. So in our previous video, I showed you how to construct a simple multisim circuit and use ammeter and voltmeters to connect to your circuit to measure component characteristics. Today, I want to tackle our past paper physics question using Multisim to verify our results. Okay, so what you want to do is start a new project. So we go on new, go to new design, click, a new workspace should open. Now let's bring up the physics question. Alright, so this is the circuit we are going to design today in Multisim, and let's read what this circuit wants us, what this question asks us to do. It asks us to use the figure to find the currents I1, I2, and I3, the potential difference between points X and Y, and the terminal potential difference, which is the potential difference across the anode and cathode of this battery. So now let's figure out what components we are going to need. To measure each of these individual currents, we will need an ammeter. So that will be 3 ammeters needed. They want us to measure the potential difference across X and Y, so that is a voltmeter, and the terminal potential difference across the battery. That's another voltmeter. So right off the bat, we know we need 3 ammeters and 2 voltmeters. Now we need the actual components for this circuit, which shows 4 resistors and 3 DC power supplies. So let's get started. So let's start by placing the actual circuit components. So we'll place all the power sources, and don't worry too much about changing the values. We'll edit them after they have been placed on the workspace. So we'll go back to place component and then return to power sources in the group of sources, and then we'll click DC power. Click OK and place the power supplies on the workspace. Every time the window reopens, just keep clicking OK so you can click the ghost image and place it on your workspace. And there we have our 3 power supplies. Now we can close. We can left click on components and hold down to drag them, so we could move them all over the work area as we see fit. Now we are going to place the 4 resistors. So we go back to place, component. This time we go to the basic grouping and we will select resistor. Click OK and place the resistors on the circuit, so on the workspace. So click OK, keep clicking OK to place all your resistors. And there we have it. We have the 4 resistors needed. So the next part of the circuit we needed were the 3 ammeters, and the 2 voltmeters. So we return to place, we'll go to component, we'll select indicators from the group drop down menu, and we will take the ammeter horizontal to measure I1 and I2, and then we will use the ammeter vertical to measure I3. Don't worry too much about the cluster, you can always move them around after. Now we need 2 voltmeters, so we return to place component, and this time in the indicators group drop down menu we select voltmeter. So we'll use voltmeter vertical in this instance to measure the potential difference across X and Y, as well as the terminal potential difference of the battery. So I just breeze through placing all the components on the workboard. It's just important to remember where you placed your parts. Now let's go back to the question and see how to organize the circuit. So okay, we have the resistor before the power supply in these cases, and resistor after. So alright, this is connected, and what we want to do here is rotate these components so that it fits in the circuit properly. So we right click on the circuit component itself and click rotate clockwise. Make sure these components are in line. Alright, so resistor, we'll right click to rotate this resistor as well, and then we'll align it with this power supply, right, and then align this ammeter on top and drag these across, making sure they are still aligned, and the circuit looks a bit neat, it's coming together, so let's just connect. So we'll be dragging and dropping wires with left clicks. Yep. In case you forgot from last video, I'm also missing a really important part of the circuit, and I need to place it after I've connected all these components. Remember, in Multisim, circuits do not simulate without a ground. But luckily, Multisim will give you a warning if you attempt to simulate without inserting a reference point into your circuit. So, Multisim sometimes does that. This circuit we're going to use today will be to demonstrate KVL and KCL. So, KVL and KCL are actually Kirchhoff's currents and voltage laws. So, if you recall, Kirchhoff's current law states that the sum of the currents entering a node is equal to the sum of the currents leaving. And that is the algebraic sum, meaning that these values can be considered negative and positive depending on what direction they are actually going in. So, let's just finish connecting. So I'll connect this voltmeter in parallel across what we consider the battery, which is this power supply as well as the resistor, and then connect this across the terminals X and Y. Time to place my ground, so I'll place component, return to sources, click on power sources and click ground to place it in the circuit. And there we have the circuit built. But one more thing we need to do, we need to edit the component values. So now we are going to put the 10 volt, 2 volt and 3 volt resistors. So this, we double click to change the value here to 10. We double click again to change this to 2. And we finally double click here to change this to 3 volts. So now we've edited the voltage of the power supplies. Now we need to change the resistance values. So there are 2 4 ohm resistor, a 5 ohm resistor and a 3 ohm resistor. So this goes to 4 ohms. So you double click, double left click to change. This should also be 4. This resistor is 5 ohms. And this becomes the 2 ohm resistor. And there we have the identical circuit. Windows 8. So yeah, there we have the identical circuit to the past paper question. Now what we need to do is actually simulate this to get the answers that they were looking for. So let's click play on our simulation toolbar. And there you have the simulated circuit. Hold on, I think I mixed up something. 4 volts, 2 volts. Oh, I've spotted an error. Well, this should be a 3 ohm resistor. Note that when Multisim, you must stop the simulation before you try to change the device parameters. So I'll change this to 3, and then I'll replay it to find the correct answers. So there you have it. This is the final circuit simulated in Multisim. Now let's return to the question to find what they wanted. So we see I1, I2, and I3 here. So now we have I1 is 1.15, I2 is 0.3, and this is a perfect instance to demonstrate Kirchhoff's current law. Kirchhoff's current law states that the sum of the currents entering a node is equal to the sum of the currents leaving. So, for instance, the diagram denoted I3 as leaving this node. So I3 is 0.85 amps. Therefore, one of these currents on top must be negative to really to be summed and give you the answer as 0.8. Therefore, this current I2 here is actually negative 3.3 amps. Therefore, 1.15 plus negative 0.3 gives you 0.85. And there we have demonstrated Kirchhoff's current law. So now to demonstrate Kirchhoff's voltage law, which is a bit more tricky, which is a bit tricky, I should say. And I actually have them written up here so you can follow up. Kirchhoff's second law, Kirchhoff's loop or mesh rule, the principle of conservation of energy implies that the directed sum of electrical potential differences around any closed network is zero. So it seems a bit daunting when you read it there, but it's really a quite simple principle. So let's consider this circuit to comprise two loops. So we'll consider this loop and this loop, not taking into account the measurement devices. Okay. So the sum of the EMFs around this circuit is supposed to total zero across these closed loops. So what we can do is include more voltmeters so we can measure the sum of the potential drops across this. So if it is equal to the negative of this, then that means the circuit is actually obeying Kirchhoff's voltage law, because the positive of a number plus a negative of itself is obviously equal to zero. So let's just copy this. We can right click on a component and click copy to copy it, and then right click. Paste, and we just get the ghost image, and we can drop this component here in the work area, and now we drag the pins here. So the value you expect to get when you simulate is actually 5.4 volts in the same way, but because the voltage drops actually oppose each other, one is obviously negative in reference to the other. So when we click play, we should see the same 5.4 volts, which tells us that this loop has indeed obeyed Kirchhoff's voltage law. Now let's try this with the second loop and see if it indeed obeys that. So now that this is a second loop, we know that this potential drop across the battery as well as the 5 ohm resistor should be equal to 5.4 volts as well. So now I'd like to drop another voltmeter on the work area. Since we already copied it before, it was already there to be pasted on the clipboard. So we'll just connect the terminals across the 5 ohm resistor, and then we'll run the simulation again. And there you have it. 1.5 volts plus 3.9 volts is equal to 5.4, which is equal and opposite to this, meaning the sum of the potential drops across this loop is also zero, and therefore it also verifies Kirchhoff's voltage law. So there you have it, guys. We have solved the past paper question using Multisim. Stay tuned for our next video, where we will be continuing circuit theory, and we will be going on to half-wave rectification. Thanks for watching.
Advertising on YouTube helps me reach engaged customers like Jenny, who's been searching for landscapers on Google. So when she watches YouTube, my ads there.
Let's learn the basic operation of the 2-channel oscilloscope to display waveforms. I have a circuit with a 1